Good evening, everyone. So far, we have finished the course, but only some tutorial problems that we need to solve just to see how things are simple. If you see basically the example problems, if you see there may be some tricky a bit, but if you apply your mind, you will be able to solve it very easily. Yeah, so we are looking at those. Okay, now uh, regarding quiz 2, grading I have started but I have not completed yet. Okay. So uh, one thing I will do, I will post the solutions as soon as possible. Yeah, so this you will know. And regarding the graded one, when I will be able to give you uh, this week, probably not possible. Only next week only. But what I will do, I will post the solutions as soon as possible. Possibly today. Actually, I will do that. And then next week early as soon as possible, maybe Monday or over the weekend, I will try to finish it. And Monday, we can I will put it in the lab. Okay, and from there you can pick up your quiz, or we can also set some time that I can come and I will be available, or you can come to my office as well to discuss if anything you think that is a problem with creating. Yeah, so sorry I could not because of lot of things are there. Uh, Dean's office keeps me occupied a lot. That's the main thing. So I can't keep promise, so that's what it happens. Yeah, so even some editing work I thought I would do, but then minutes come and then I see the way it's written, I don't like it, and I have to write myself. So I had to do all kinds of job, name it. Well, faculty is supposed to do everything from peon to CEO. It is in the profile lately. We have been director, actor, videographer, cinematographer, you name it, everything, script writer. So these are the new things that we learned. And the video editing. Yeah, but this is how it is, and we start enjoying that way. But only thing is, it takes time. Because of that, I could not complete. But I promise next week as soon as possible. Okay, now 10.3. I think two problems we have solved. So we will solve this 10.3, and it says that you have a beam which is like this one, and top of that there are yes, like that. Okay, so x, y, and z. This is x. This is y. Yeah. So what is the difference? Here there is a beam, but there is a spring as well, and the stiffness is also kx. So this is a stiffness which is distributed. So what it is a consider a beam on an elastic foundation. Yeah, formulate the strong and weak forms. So elastic foundation means that there is a spring which is distributed. So meaning, what is the meaning of that? This kx itself, it depends on the for unit area will depend on this one. So the kx, the unit will be what? This kx is Newton per Newton per meter per meter. Yeah. So meaning that if you cut from here to here so big, like let us say this one, this will have Newton per meter. So that if you stretch more you get the force. Yeah, so stiffness is there, but this is distributed. So the units unit is Newton per meter square, right? Okay, so distributed stiffness. Just like distributed load you have, yeah, you have distributed stiffness. And this will bend because of it. And how you are going to solve it? You are going to start with the fundamental equation, you remember, and that was like you have px here, and then you had the v plus dv over dx times dx. Here you had v, and then you had moment m, right, plus dm over dx, and here you have m. But these are original, remember? This was from here to here dx. Now you also have this. So you have also force here, which is going. So this is the px. So because of that you can have in the middle, you can apply. So you can apply in the middle. This will be px times dx, right? And here you have kx times dx times uy. It will depend on the vertical displacement. So it will be k x times dx times uyx. More the displacement, the more will be the downward pull, right? So this is how it is. Yeah. So in effect, what you get is basically what you get is this way. This will be px minus kx uy multiplied by x, and the rest remains the same, right? Rest is like we have v m v plus dv over dx and m plus m over dx.
How are you putting the px force in the center?
It's very small, so it is so. It's very small. So you can assume that it's exactly constant at that point. That's right. Okay. Now you repeat everything, and what do you get? You get e to power 4, right? Uy over e over ei, primary variable d square uy over dx square, right, is equal to px minus kx times uy. We will get this answer. Okay, so your equation is basically with square over dx square ei d square dy over dx square plus kx multiplied by u. That's it. So this term is such like you encounter in like convective heat transfer, remember, multiplied by T somewhere. Here you have multiplied by Y. Yeah, so this will contribute in STFs. Yeah, right? You understood? Okay, so although this question does not ask you how to calculate, okay, maybe a strong and weak form. Okay, so what will be a strong and weak form? In addition to what you have, you will have corresponding to this, right? So Wx multiplied by kx multiplied by u yx dx and integral 0 to l. That will be just added, and hence the kij will be integral 0 to l.
DNI square.
Okay, ni dx square ei d square upon j over dx square dx plus
Integral 0 to L.
yes
Dx.
dx
Ni.
ni
Nd.
x and j.
Dx.
Excellent. Yeah, that means you have followed this course. Yes. That's it. Very simple. Okay, we'll move on to next question now, and this is 10.4. Consider a tapered beam element. Beam has a constant thickness T and linearly varying height. Derive the steeping matrix and tapered beam. Okay, so what it says is you have a beam which is changing light. You have HL and then 1 minus x over 2L. L 1 minus, this is the height at any here. This Hx is given by HL 1 minus x over 2L, where this is so what you have to do is, this is node number 1, node number 2, and we have to find out the stiffness matrix K. It's easy, it's not difficult, everything remains the same, only thing is you have I is not constant. That only tells you I is not constant, right? So your Kij will be 0 to L d square n I dx square E I as a function of x. That's it. E square n j over dx square. Now you have to find out Ix is equal to. So if you cut anywhere, and this will look like this, where this is the height, which is hx, the thickness is t, which is given. Yeah, so like this one, you have to find out I, and Ix will be equal to, tell me the value. Ix will be 1 over 12 t hx cube. Yeah. So I will simply 1 over 2, where you have HL square cube, multiplied by 1 minus x over 2L cube of that, multiplied by t. So you have this going here. That is all. Then you integrate. Yeah. Only thing is the order of the displacement increases now, right? The rest remains the same, everything same. In fact, 10.5 is about this only, but you have to solve the problem, right? So there is some problem given, but what you have to do is you have to integrate, or integration here. Again, you remember this is 1D, hence you can apply the Gauss quadrature formula, 1D formula you can apply, you can integrate it. Yeah. So only K while calculating K, you use Ix equal to this, and everything remains the same, so it's not challenging. Right? This only I was the trick. That's it. Okay, so you take care of that. Now 10.6. And guys, remember, whatever you learned, you can combine all of them together. Yeah. Apart from these, let us say, I'm just remember, came something to my mind. That's why I'm saying. Let us say, since you have studied the plane stress problem, so you can do something like this, right? What will you do? You can have a plate. Let us say you have a triangular plate, right? And then what you will do in this case? Maybe you fix it here. Then there may be a beam which you are building here. Then it's builded here, right? And then you may have a truss which goes from here to here, and it is pinned like this one, right? And then you are going to apply your load. See, this is truss element. You use it, but truss element, but 2D truss element. Remember, you rotate it. This is beam element. This is 2D or plane stress element. You can all apply, right? So formulation will be different. You make its Stephenson matrix for this one, and then you combine. When you assemble, you have to combine them together. That's it. What you have to do. Now you will wonder the beam that you have to rotate, right? The rotation matrix you have to apply. So if you have a beam, you have derived for this. Then you are going to rotate it from here to here. So simple. Any vector which is here, let us say like this, and when you rotate, it becomes something else, right? So same rotation that we did during the truss element, similar kind of thing you can apply here. And we can have a beam, you can have a rotated Stephenson matrix. Yeah. So those things, extra things I'm telling. The way we studied the truss element, we had only 2 by 2. Remember, we had U1, U2. Then we put it in some angle. Then we had this and this and this. So this becomes 4 by 4. Here, what do we have? In our case, we have like this, and then we have U, Y, and theta. In this case, what happens? This is will be like this one, but actually, what we have is like this. So combination of the two will give us the displacement perpendicular to this beam. And apart from that, we have moment. So we have now three here, 3 here. So 6 by 6 matrix here. Whatever theta is here, it will same theta will be there. But the displacement here, when you rotate, this will have components in the 2 directions. Right? The way you did for this guy, similar you can do here. Same rotational matrix you can apply for this guy. Okay. Only difference is there it was like this. Now this becomes like this. In this case, it is like this. Here it becomes. I'm telling you some extra things, So the beam not necessarily you have to take like this. You can also rotate it. For that, you have to apply the rotational matrix. The way you rotated the curves, you have to rotate the beam. Yeah. If you keep that in your mind, that's it. Yeah. Such problems are not probably here, but I'm trying to combine them together. Not making it difficult. Okay. Difficult, it is nothing. Difficult, it even goes a lot of difficulties. Yeah. So, since this is the final week, so I also have to introduce you to some little bit complicated like the future work, right? So also what happens is, let us say there are some non-linearity involved. So I will just yeah. So even when you work with abacus, you can have non-linear geometry. That's one thing. It's a non-linear material. So right now, when you say non-linear material, that's easy to explain. What you do, you have a strain here, you have a stress here, more strain, more stress, right? You increase the strain, you have stress, right? So you call it as slope is Young's modulus. Non-linear material, this may be something else. This may be like goes like this and then goes like this. Polymers will behave like this. Okay, so what is the plastics will be like this? Yeah, or polymers. So of course, you can do this one maybe for a small displacement, but bigger displacement it will have something else. So for a small displacement, still it will be linear only. Yeah. So all kind of things are there. Accordingly, you have to. There's some algorithm. What you do, you finally. In this case, what happens? If a stress is given somewhere, and you find out the strain, how? This is because this sort of your force is given, you are finding out the displacement. Here, if the stress is given, you are finding out the strain. And you know the slope, E, it's easy to do. E is like a stiffness. Right? What do you call it? Sigma equal to E times epsilon. It is something like E times epsilon equal to sigma. It is something like K times U equal to F. So epsilon U equal to K inverse F. It is like epsilon equal to E inverse sigma. The E and K both are equivalent, basically. Right? So in one go, you get the answer. Now, here, what do you mean by K? K will be equivalent to the local E. You call it tangent modulus, comes into picture. Here E is different, here E is different, here E is different, here E is different. Meaning that here K is different, here K is different, here K is different, here K is different. And hence, you cannot proceed like this. In one step, you cannot do. You cannot just invert and find out. How do you go? You start here. You target this. Yeah? And then what you go? Newton Raphson. You go here, you find out what the value is, right? Then from here, you go here, then come back here. From here, then you go here. Keep on doing like that. You remember Newton Raphson? So Newton Raphson. The goal is to, you start from here, you reach here, then you reach here, then you reach here, then you reach here. Yeah, you go in the steps, and that's why it may converge or not converge, and hence it will tell you whether it has converged or not. Right? You can find out. But the bottom line is, in one step it will not do. Hence, when you work with the abacus, it asks you how many steps. Then you will think, you don't need any steps. How come the steps is asking? Right? So this is asking because it wants to have some iterations, because the material non-linear. It has to do some different steps, and hence it is doing like that. Nonlinear geometry is also the similar. Similarly, it comes into picture. And nonlinear geometry is like say you have a beam and you apply a moment here. Yeah. Now displacement, if you see, if you take just a single element like this one, and I'm talking about nonlinear geometry now. Linear geometry means displacement will be, sorry, you have like this, right? And then your displacements are small. Nonlinear geometry means linear geometry means displacements are small, basically, right? When there is a big, let us say, you apply a moment like this, right? And then what happens? There will be displacement because of that. Yeah. So this will have some k value, right? So you can find out what will be the theta here, right? So m will be equal to k times theta. So m is proportional to the theta. So whatever you give here, theta, this theta or k, they will be related. Yeah. Okay. Now what happens if you have high theta equal to m over k? Bigger m, bigger theta. Bigger m, bigger theta, right? Right? And your y will be what? Y will be, in this case, or uy will be what? Yeah, this will be proportional to theta, right? Proportional to theta, right? Now, what happens in real life? If you apply pure moment, this will go like perfect circle, right? More load, go like this. More, it will like this. You apply more, it can be like this. This you cannot predict. Based on the current model, you cannot predict if you apply the load, it will be 4 or 5 turns it can take. You cannot get this. Yeah. Why? Because theta is supposed to be very small. You see here, theta is like going not at 36, 360 degrees, goes even multiples of that. It's very big, right? So this is nonlinear geometry here. You cannot solve by this, but it gives you error. What it tells you is, in this case, your displacement will be infinite, more M, more displacement. Here you will predict this goes like this. If you apply a big moment, then displacement is infinite. But in real life, you more moment, more turns. Right? So this is nonlinear geometry. Hence, you have to formulate what you call it large displacement formulation. Yeah, and here you go into nonlinear elasticity. Yeah, and here you go to get some terms, second Piola curve, stress, and what is the equivalent strain? Huh? The complementary strain is also non-linear. Yeah, maybe green strain. Different subject. Okay, so I reach here. After that, you have to go. Okay. Okay, so the course doesn't allow to go further. Okay, but this is the where I tell you that you studied the anatomy analysis, not enough. You study more. Okay, but this tells you what to do. If you want to go into details, the formulation will be different, and it will be difficult as well. Yeah, and right now there is no course on nonlinear finite analysis, but I think at least there is a master's course on theory of plasticity, right? You call it advanced solid mechanics. I think this is taught there, right? Some these things will be there. Second level of stress and all. So which is based on a stretch ratio, the distribution. Anyway, so this I just thought that I give you some glimpse that there is a way forward. So it's not that's ended. You learned everything. So it keep on going. Okay. Any question, guys? Okay. Also, what we did not study is the time dependence, right? Viscoelasticity we did not learn. Yeah, so viscoelasticity is another thing that is more close to the vibrations. So their viscoelasticity comes into picture. It's a mass of just let us say a beam which is made of a rubber material. And now it also have mass, so rho comes into picture. Then it will also have some viscoelasticity, so that we call it eta. Yeah. So finally, the equations will be in terms of something like this, right? X kx cx dot plus kx, and that which is a function of time. That comes into picture. Of course, if we are talking about materials, so rho will come into picture. C, we are talking about the eta term. K, which is length moment. They come into picture. Okay. Instead of x, what do you have? Strain comes into picture. So you have x is nothing but some strain will come into picture. So strain weight will come into picture. Yeah. So just how it is. Okay, now 10.6. It is telling you that there is a beam like this. Yeah. Anyway, details are given, but it is telling you have to solve it as a two to know the elements. Okay, so some dimensions details are given, but how will you do? B H L. So you have from B from here to here, B from here to here, L H. It's very easy. If you have to find out Kij is equal to, how do you write? D square Ni over dx square E, and then I as a function of x, d square nj over dx square dx. Your I is changing, that's it, right? Your I is different, and there will be a, from here to here you have, from here to here means this is B. Here you have some I1, here to here you have I2, then you have I1. Okay? You calculate what is the value of I here, calculate what is the value of I here. Both will have different I here. Right? Here it is, you remove this, whatever the value you get here. So what I2 will be equal to I1 minus 12, 12 what? You will have thickness T and H minus 2A. L minus L minus 2B क्यों? सेक्शन यहाँ लगता है. You are looking from this side. ऐसे लग रहा है. And then this is 0 to L. So Kij is equal to 0 to, now you will do here 0 to B, twice of it. No. It will be different because value of Ni will be different. So you cannot write like that. So 0 to B, so D square Ni over dx square E I1, right? And then D square Nj over dx square dx plus B to
L minus 2.
L minus B. Then you have D square Ni dx square E I2 D square Nj dx square dx plus L minus B to
L.
L. D square Ni dx square E I back to I D square Nj over dx square. Okay. The small tricks, here and there. If you have your basis clear, you will know immediately what you have to do. 10.7. So you have here, then you have here, and then another last one. So I think you have roller here, roller here. Then you have so this is x is equal to -2. Some value -2 in there, and then you have a force somewhere minus P equal to -10 kilonewton. I think this was a kilonewton only. And then somewhere it also has moment. M equal to 5 kilonewton. There is a moment here. M 5 kilonewton. EI is given so first it is telling you assume two elements one. Okay. What is the complicated thing here? The EI is a constant. Yeah. If you are given this problem, where do you think you will face difficulty? Interpreting?
Point load and
Okay. So only if you know the point load. Yeah, so point, I think it's exactly in the middle probably. So let me see the x equal to 2, so in middle, and then x equal to 6. So it's at the middle one. So here it is 4, from here to here it's 2. Yeah, and similarly from here to it's 2. Yeah. Okay. So how to distribute the load, right? So as far as this is concerned, let us say we talk about the first element, and the P part we know already, right? You remember the what we had got was if you have Px which is equal to P naught, so in this case you will get here P naught L over 2, here also you get P naught L over 2, right? We have calculated yesterday, right? Yesterday only. As far as Px is concerned, is equal to minus P naught minus O, that's why both the presage you see down. Yeah? We have just distributed load. We are distributed between these two nodes only. Then we also got the moment, right? And moment we had got was here it was positive or negative. So here, like this one, so I think it will be here and getting it, something like that. Just check. So you will get P naught L over 12 L square maybe. P naught L square. Huh? This will be minus. There it was, force was upward. Okay, here it is downward. Yes, it will be just opposite of it. Yeah. You can see since forces like this one, it will try to have a moment both the sides because this is going to give a like a sagging type of moment, right? So if you have like this one, this is going to sink in the middle. Right? So it should be something like this one. So this you can do the usual method. Only thing is, what about P? Yeah, so let us say because of P, we have these four forces. Which one? So we call it, remember, we call it, let's say P1, and this call it M1, let's P2, and anti-clockwise, this also. So M2. What will the value? So P1 will be equal to 4 by 0 to L, yeah, N1x multiplied by P, whatever the value of P is, but this is a point load. So you can have it's a direct delta function. We are writing as a function, so L, and you have in this case x minus 2, right? Or x minus 2. Right? And then you have here. Which will be equal to what? N1 at L over 2 multiplied by P. That's it. Right? Now what is the value of N1 at L over 2? We have to find out. This is not linear, so we will not get half. It will be something. Those values will be, you have to find out what exactly is equal to this one 1 over L cube. So here x, so L minus L square.
So N minus N plus L.
Yeah. So this is N at L. L over 2, N1 at L over 2, right? And which is equal to, so this becomes 1 over L cube multiplied by here 4 and then 2L, right? So you get L over 2, is it? 1 over 2. Yeah, you're getting 1 over 2. How come? I take my words back. Okay, so very good then. It is equal to P over 2. Where P itself is equal to minus 10, so equal to minus 10 equal to minus 5. So minus 5 goes here, minus 5 goes here, right? And then then next one also you can write the same way. N2, similarly for M1 you have to write M2 now. So this is the way you do. Similarly for this also. Similarly you do for this also. But this is a moment. What will you do now? I have no idea. You have to figure out. Second question is actually based on this one. You see now you are facing difficulty because of it. But you could have solved if there were a node there. Hence, if I ask to place a node, we will place a node here. And then you will have three elements, 1, 2, and 3. And then it will solve.
It's really given one element only. The one.
Pardon me?
That if we have divided it into elements and that point is node, then we include the one only on one side, right? Only in one element. They remember.
Yeah, well, you always assemble it. In global matrix, it will appear at only one point. So you put later, after composing the global force vector, you put there, not any individual element force vector, no. Element force vectors will only have distributed loads coming because of it. Yeah. Or if it is end, then you can put the end forces. But if it is in the middle, you don't do it. Because this is a kind of a body force then. Yes, hence you don't do it. If it is at the node, then you don't put in both of them. Yeah, you put at the end. Okay. But in any case, if you are given like this one, if you have to solve, how will you solve this? If you have only two nodes, let us say we have only one node like this. And we apply just a moment here, then what will you do?
Reaction force upward on this side and
Then what will happen? It will, if you see, it will have, if you see the bending moment, how will it look like? It will not be constant, it will be maximum here, it goes, this is the bending moment. Right? So you will have the shear force, which slope of that, right? So it will be because of that. It's negative. Yeah? So this is because of this Cote's problem basically. Yeah. So in order to do that, it will give you error basically. You cannot possibly solve with the, if you have just two elements, then you cannot do it because mechanism does not allow it. It is not in terms of force, that's why. But what you can do is you model it as a, you have a point here and you have force here there. You have force here. And you take, right, some distance, let us say small a, and then you have some force applying, then force here, right? And then m will be equal to f. Yeah. So you are imposing this kind of condition there, right? And then automatically then you can solve now, right? But here a will be very, very small. You can assume a is small, and you create a moment, artificially creating a moment basically to do it. Yeah. And that way you can solve them. And you can also see now, if you have here like this and have like this one, then what happens here? Because of this, there will be a shear force. Because of that, there will be a shear force. And one moment. But this is artificial. You know, you have to replace only moment. You have to replace with the force. This is the way you are going to do. There's no other way to do. Alright, guys. Yeah. Where a tends to 0, you will say. Right? Such a way a tends to 0, very, very small. Okay. Yeah, any question? Rest you will understand. Rest. 10.8 quickly. And what it is telling you that you are doing the frame element. Yeah. So what is telling you, you have to derive the frame element. That means you have a force, you have a ux here, because you have a force basically, that's what it means. And then you have this force as well, what you call it, a moment. So this is a V, this is M, this is V, right? This is M, M1, M plus dm over dx. Then you have V plus dv over dx. Then you have axial load F, and here you have F plus df over dx. Right? And then this has this will have px as well. This will also have the px. So there is an axial load as well, right? So then in that case you will have to combine all the forces, right? So if you have body force, let us say, right? So there will be some body force. Then which will be something like this. Then there will be a transverse load as well. I think body force probably is not there in this case. Beam and a bar, both times. Yeah, it does not have a free body diagram. Even body force you can take into account as another. Also you can have that. Yeah. So now what happens? You will also have a. This has to be equal to 0, right? So you will have the forces that has to be equal to 0. So you will automatically have this guy, right? So you will have in this direction only the total force has to be equal to 0. Right? So finally, your result will be basically that this will be a combined, as we talking about yesterday. This will be 3 by at one node there will be 3 degree of freedom. And what you will see that they are independent of each other. So force in x direction is all 0 equal to 0, and hence what you will see that df over dx plus b x times dx is equal to 0, right? Or df over dx, right? Plus dx equal to 0, or where f is area, where f is equal to area times stress is equal to a times a times, right, d u over dx. This is ux. So put the everything, get d over dx a dux over x plus dx equal to 0. So you get one which is independent of u. Uy is not appearing there. So this is entirely independent equation, right? So that means actually you can separately you can calculate and you can combine both. That also true, because they are separate. They don't like they do not interfere with each other, right? So hence you can. So this you get from there, and what the other equation is d square dx square I d square uy over dx square equal to 3x. Right? This one is for the other degree of freedom. So this degree of freedom is independent of this degree of freedom. This rotation and the transverse displacement, and hence you can independently calculate. But when you are calculating the stress, then you have to combine. When you are calculating the stress, then you have to combine. Yeah, because the stress will be whatever stress you get from here. So let's say this is because of the F. So this is F, and then you have minus Y, and then what you have? E. What is the strain? The strain is minus Y A square Y over dx square, right? And then E times Y E square dy over dx square. This will be the final stress, because this coming from here, this is nothing but E times d ux over dx, right? Minus ey d square dy over dx square. So this is the relation. Final sigma will interact. This coming from the axial stretch. This is coming from the bending. Say they will combine together. Okay? Only that you have to keep in mind. Displacements won't interact. Stresses will interact. Any other question, guys? Anything? Okay, we'll stop here. 10.9 is about the frame element. Yeah, so same thing that we have done. You can rotate. I think this the next one is 10.9 is about the rotation itself. So we will meet on Friday. Yeah, and that day. Not tomorrow. Okay? So tomorrow no class, but Friday we will meet. And if you have any question, you can ask. Yeah, this is for any question you have. Anything. Yeah. Okay, those who are online, any question, guys? If not, tomorrow there is no class. I will see you guys on Friday. Okay. Okay. See you all.